This video is running in real time, so I'm not going to talk for 40 minutes. So just skip ahead to where you see these little blue bits, and that's where the talking occurs. So the first thing you'll probably note is it does take a long time. I'm assuming it's aluminium. So the specific heat of aluminium is 0.9, so it heats up. So the specific heat is 0.9 joules, so that's how much heat it takes to raise 1 gram by 1 degree Celsius. So it heats up and cools down very, very quickly, whereas water, it's 4.18. So water takes a long time to heat up and a long time to cool down. So 4.18 joules of energy to raise 1 gram by 1 degree Celsius. And so that's why this takes forever. Now, the first thing we're going to just note is that the density of water and the states of water. So you can see that water is unusual in that its solid is actually less dense and it actually floats. In most substances, the solid is more dense and will sink. And so you can see that's because there are hydrogen bonds. So we call them interparticle bonds for the time being. The white parts have a positive charge and the red parts, which are the oxygen, have a negative charge. So the white's always hydrogen, red's always oxygen. And so those pos and negs stick together. Now, when it is cold enough, they can actually form those bonds. But when you have it heat up and there's more kinetic energy, what you're going to find is that they will roll over each other, and those little crystals and those gaps there will collapse, and the hydrogen bonds will form and break as they collide into each other and roll over each other. And so that will be in the liquid state, and that's why the liquid is more dense and the liquid sinks. Interesting enough, if you notice here that the time when it is the most dense is actually when it's 4 degrees, because between 0 and 4, there still isn't a large amount of kinetic energy, so there still is some more formation of those hydrogen bonds in a static sense, even though they are rolling over each other. And so you can see there's not just one black and white change. So the density of water actually peaks at 4, and then as it heats up, there's more kinetic energy, and so they are rolling over and they're sort of separating out more because they have more energy bumping into each other, creating more space. And so the full density curve is here, and you can see there's a little bit of complexity to it because there are at least two acting forces going on. How easily the hydrogen bonds can form and how much the kinetic energy is disrupting those bonds, intermolecular forces, those bonds forming to create those extra gaps. Another thing you can note, even though we've just started, is that there is boiling occurring already at the very, very bottom of the beaker, because the beaker is basically just solid ice, and then there's a little bit of water at the top and ice at the top as well. And so that little tiny bit of water at the bottom is boiling because the heat basically can't transfer through the solid very well because it's static. Whereas in a liquid, they can roll over each other and they can transfer quite well. And so that's an issue with the mixing. And we'll see later on that will also affect the accuracy of this experiment. There's an anomaly that we can jump to. Okay, you'll see there was a spike, a strange spike in the graph. Now, this is probably a good place to describe what actual temperature is. So the temperature is actually just the average kinetic energy of the molecule. So you can see from this graph here, energy, which is kinetic energy that we measure in joules. It's the heat energy, so the energy of the movement. And you can see that even though you have like a warm sample and a cold sample, so a cold sample have a lower average kinetic energy, so a lower temperature than a warmer sample. There'll still be molecules within that sample that are very, very hot and very, very cold. Not usually obvious, but it is obvious when you have incomplete mixing, like you can see in the beaker here. Another thing to note here is the water is actually at less than 0, and so it is way below, well, it's below the freezing point. And I'll talk about other things a bit later in this video, but looking at that, it's quite common also to get a boiling point that is above 100. We'll worry about, but I'll talk more about pressure and stuff later. And so that's called freezing point depression, and it can also lead to boiling point elevation, which is why you add salt, a little pinch of salt to the water when you boil it so it goes higher, so the food cooks quicker. And so what's going on is because there's salt, there's sodium and chloride ions, or any other contamination, actually, it could be any sort of chemical in there. It binds quite well often to the water molecules, and so that can prevent it from forming those spacious crystals, those low energy structures, and so it can't form a can't form a solid very well, and so it takes a lot more energy to be removed in order to form those solids, so to become an ice. And in a similar way, it's the water molecules are binding quite strongly to the ice, so it's hard for them to escape as well, and so that also increases the boiling point. So freezing point depression and boiling point elevation is what salts can do to water, specifically because the salts, the positive and negative charges on the salts, positive and negatives, cause quite strong bonding. Now, at this point, the temperature starts to rise even though all the ice hasn't melted. So that is obviously an issue with the mixing. As I said before, it was boiling at the very bottom. And so I need to start mixing it around to make sure that the temperature is the true temperature, and it should stay even, as the heating curve will have shown you. So what I'm doing, you'll have to skip ahead, and you'll see that I start mixing it. So when I start mixing it, it brings it back down to what the true temperature is. We start to mix it here, and it should come down, hopefully. All right, and then when I just leave it to the bottom, it's it's almost touching the heating pad. and so it spikes up again. And so that is not the true temperature of the entire substance because there's still ice. So there's uneven heating going on all in there. And so I'll stop there and you'll see later on I'll keep mixing it. And that will keep the average more accurate rather than me using the thermometer and just measuring the bottom. And later on, you'll see that there are convection currents. So once it heats up enough, you'll look at the beaker as it heats up. It starts further on in the video, and you'll see that the liquid itself is rising and falling. So I stopped mixing it at that stage because the convection currents are mixing the heat and heating it up. So convection, conduction, radiation are the three ways heat is transferred. So the heat is conducted touching. So the kinetic energy, the particles are vibrating and hitting from the aluminium into the water. Radiation, you can actually feel that's electromagnetic waves on this electromagnetic spectrum, which includes light, infrared, microwave, etc. You can feel the heat with your hand, and as you're sitting there, going through space or through air actually, but can go through a vacuum through space. And the other way is just the rising and falling. And so that happens later on in the beaker. You'll see stuff go up and down. So as it heats up, it expands, it's less dense and it rises. And then it goes to the top where it cools down and becomes more dense and sinks. So it forms this circular mixing. And so that's convection, all right, based on density differences because the particles are spreading out because they're hitting each other more, creating more gaps. So convection, conduction, radiation, all right. Okay, now here's as good a time as any. Just talking about the change of state, have a careful look as it progresses. So as it heats up more and more, you'll find that you'll see wisps of vapor come off more and more in both the both diagrams, their side view and the top view. And so that is evaporation. It's just occurring at the surface, and it's occurring throughout. It even occurs in ice. And it occurs at all temperatures. Whereas what we're going to see at the end is boiling. So you're going to see that the vapor forms within the liquid itself, and it's at a set temperature, which will be 100 degrees because it's a pure substance. So we say, you'll know from if you've watched this video, that it's not 100% pure. All right. And so the proper definition of boiling is when the vapor pressure is equal to the external pressure. And so if we put this in a vacuum, it would boil at the room temperature, and you'd see bubbles form inside the liquid as it expands, because there's no external pressure from the air pushing down on it. And so it also affects it also affects this experiment. This experiment was about 1 atmosphere. I checked the barometer, but low and high pressures that come through, which is good and bad weather, can affect the boiling points by a few degrees even. So pressure is another factor that has to be taken into account. Another thing also is the evaporation actually cools the liquid, because the most energetic particles are the ones that can escape the attraction between the forces, and therefore your average kinetic energy of the particles in the substance will decrease because you've lost the ones with the most energy. And so humidity also has an effect on that. And so you can see here from this diagram that if you enclose it, the rate of evaporation will equal the rate of condensation if it's a closed environment. And if it's not a closed environment and it's very dry, the evaporation will be faster. And so that's another factor that you need to consider, another variable that wasn't measured and wasn't controlled. And so that is an issue as well. Now, as you can see here in this video, there's little bubbles that are forming, but it's well below the boiling point. It's like 10 degrees below, or 5 degrees, depending on where we are at the moment. So have a look at the part 2 video that's in the description. That shows you that the nitrogen bubbles coming off, and then I reboil it, and you see that at the same time, same temperature, that this does not occur. So it's not just the salt or soluble salts contaminating. There's also the gases from air that get in there and dissolve into the water, and so it's not pure water for that sense as well. And the part 2 video, which is actually done first, it also shows you the rate of cooling that goes on and how quickly it cools, and that the effect of that on your experiment. So that is quite useful, and it's a much shorter video too. All right. Okay, now that we're coming close to the end, and we're going to start to see just the lift, and then the second plateau coming out, which will be the boiling point. So at the very start, we saw just the ice going from 100% ice, slowly working its way down to 0 ice, and that's a plateau. So that's the melting point. And so all the energy goes into breaking those static bonding, and so they can roll over each other. And so until all of that's done, the temperature does not increase, and that is the melting point. And that occurs, and you can see that physically, not just by measuring the temperature, by seeing 100% ice go to 0% ice. And we're nearing the point now where it's just gone constantly up. It's going to level out now, and it's going to stop increasing in kinetic energy and sit at 100. And all of that liquid is just now going to turn into gas. And if we could collect that gas and heat it, then we'd be able to see the gas go from 100 upwards. All right, just the last point. This is just for a pure substance. And so you can see this one's a cooling curve, not a heating curve, so going in reverse. There's plateaus where they sit at one temperature. If you're going to use something that's not a pure substance and it's a mixture, you're going to come up with this graph here, and it's not going to have these plateaus. It's just going to be sort of one continuous line. And so you're not going to be able to see, you might be able to see some leveling out. You might be able to get a large range of where it might be, but it's not a pure substance, so won't have a single boiling and melting point. Okay, so for pure substances only, and it also helps you indicate whether the substance that you're experiment heating is actually pure or not. It's one test of a pure substance. So solutions and mixtures won't give you this nice plateau. We have mentioned some contamination, and that's explaining most of our errors in not being this perfect graph that we are looking for, that we can see in these diagrams here. So just to close off, I hope you appreciate all we're doing is changing an independent variable, which is time, and measuring one other thing, which is the temperature, which is on the x. So the x-axis is the change in time, and the y-axis is the change in temperature. And that's just one dependent variable. You can tell about the depth and complexity of something that is so simple. So can you imagine all the other experiments that you're going to move on from here? Because this is typically a year 7 experiment, just boiling water. But you can see that it takes quite a lot of understanding and a lot of depth to understand something just so simple. And so that's why we never go beyond one dependent variable. Even when we do this, we have a lot of controlled variables that we're dealing with to try and really understand what the hell's going on and what the relationship is. Okay?